So we start the lecture on clustering. So clustering is a prototypical unsupervised learning algorithm. So the idea is to identify groups of data that behaves in a similar way. So here we would have a representation of that. So once we have a set of objects and we can describe those objects with a vector of features, so the point is to identify objects that behave similarly. So for instance, all these vehicles have been grouped according to where they go. Okay, so for instance, we can, by clustering, gain some insight into the structure of the data, so that helps to interpret what the data is telling us. So that also helps us to discover patterns in the data, and we can also use clustering to find highly correlated features or highly correlated variables. So we can do the clustering at the level of observations. So we can say all these objects, according to these six variables, they have similar features, or we may cluster the variables. So we may do an analysis by rows, or we may do an analysis by columns, and then we would say, well, these two variables, they have similar behavior, or this variable doesn't have a similar behavior to the rest. Then here are a few examples. So for instance, this is the demand, the daily demand of electricity over years, over the day, but then we have a time series that takes several years. So we can make more and more zoom until we find, for instance, here this weekly pattern. But then if we submit every day the pattern that we see in every day to a clustering analysis, we may discover, for instance, these four distinctive clusters. So we see that winter Mondays behave differently from summer Mondays. So for instance, we can see here this peak here in the late hours of the day. The same happens for the weekdays, the rest of weekdays, Tuesdays to Fridays, and then Saturdays, they have a different pattern with respect to the weekdays, and also holidays, they have a different pattern even to Saturdays. And we may use clustering also to find different patterns. For instance, in the electrical vehicles charging, so we see that most of the charges are performed during the night, so after 5 or before 8 in the morning. So we can find what kind of user this particular vehicle has, so that we can optimize the electrical distribution to each one of the different areas of the city. Then this is also curves of quantity and price of the Spanish day-ahead electricity market. So these are called bidding curves. So how much electricity you're offering and for which price. This variable, this quantity, has been normalized so that it can take negative values, otherwise it wouldn't make sense. But then what we can find, for instance, if we try to find patterns here, is that we find all these distinctive patterns, and then every day falls in one of these patterns. Okay, so there are many different algorithms for doing clustering. Probably the two most known are k-means and hierarchical clustering, and some other very much used are Kohonen self-organizing maps that we will not see, and neural gas. So the key issue in clustering is defining similarity. So when do we say that two objects are similar to each other? And for that we need similarity distances. So there are many different kinds of distances. So, and distances, depending on whether you want to cluster the observations or to cluster the variables. So let's say that we have a number of observations. For each object, what we have is a vector with p variables, and then we define the distance between two observations as the L norm of the difference of those two vectors of each one of the components. So we go over all components, and for each component we apply a function w. This function w can be simply the identity function, so it would be simply the difference between the two components. And then for instance we compute the absolute value of that difference, power it to the power L, and then sum all of those. For all the features we do the same operation, we sum all those results, and then we take the L root of that sum. So for L equal 1, what we have is the Manhattan distance. For L equal 2, we have the Euclidean distance. For L equal infinity, we have the maximum distance. So there are many possibilities, and this is just one of the possibilities. There are really many possibilities. And for instance, for categorical variables, you need to construct a table of how different every pair is from each other. And then for variables, what we can have is that for instance, we can define the linear correlation coefficient. This is the Pearson correlation, and then the distance between two variables is the 1 minus the correlation. So for instance, when you do clustering in MATLAB, you have available many different kind of functions to measure the distance, and then depending on whether you want to have a clustering of data or clustering of variables, you should use one or the other. The problem with the distance is that depending on how you define the distance, it may be sensitive to a scaling of variables. So for instance, if we compress the data in horizontally, we may find these clusters, while if we compress the data vertically, we may find these clusters. There are distances that are insensitive to these variable scalings. So for instance, Mahalanobis distance is insensitive to this, but we will not see it during this course. Then we can also find this problem of finding different clusters depending on the scaling. So here, for instance, here we have a variable x1, x2 that goes from -4 to 4, -4 to 4, and when we scale the data, then instead of these clusters, what we find is this other cluster, and this scaling has been performed by standardizing the data, which is a pretty common operation. So we can have a lot of problems with our distances if we don't take care of this. And for this insensitivity to scaling, one of the best options is Mahalanobis, that uses the covariance matrix in kind of matrix distance that uses the covariance matrix as the weighting matrix. So this is all for the introduction, and then in the next sessions we will see specific techniques.